Okay, so we have finished the first part. The first part was somewhat the community view on principal component analysis. And you can basically follow this deterministic teleconnections, coherent teleconnections idea, and I think it's absolutely okay. I would also do it, and I think it's a way of approaching data because in our data there is patterns, there is teleconnections, and it's interesting to find out how they work. And you can work with the deterministic view. But what I would probably say is that a more efficient way of going at this is starting with this stochastic continuum view. This is the way that I would look at the data and the way that I would probably approach this. And there's actually, if you look at my webpage, there's some examples how I actually then did it. There's a number of publications where I use this more stochastic continuum view. So now I show you a slightly different view, which I think is a better way of looking at it. You eventually can come to the same teleconnection conclusions. So you can, from both views, with the deterministic mode view, you can get to the right conclusions, and with the stochastic continuum view, you might get to the same conclusions. I just think that the second approach is more consistent, and it's also more similar to the way that we actually look at time series, the way that introduced to you the stochastic climate model. So let's start with a null hypothesis for this spatial noise. So when you read the literature about modes of variability, what is surprising is that people look at the data and they apply a method that actually finds pattern. And they don't ask the questions, are there patterns? This is already assumed. The assumption is always there are patterns. I only have to find a smart way of figuring out what the patterns are. But I think it's probably more useful to go a step back and think, are there patterns? Because if I'm more objective and I go more backwards and say there's just noise, there's no structure, I might be more open to find structures which are not just a structure that the statistical test method shows you. Like if you apply different methods like cluster analysis, EOFs, or neural networks, they like certain patterns. And you will present your data in these patterns. But it might be better to go a step backwards and ask the questions, are there patterns? Or asking the questions, are there any modes? So you assume at the beginning that there are no modes. And you need to be convinced that there are actually modes. So in our climate systems, there are modes and patterns. But often it's better to start with the idea of there are no modes. There is no pattern, and let's see if we find something. So the question is, if you want to approach it like this, what if there are no patterns and no modes? What would my data look like? What would my statistical method like principal component analysis look like if there are no patterns and no modes? And I'm starting from this assumption. What if there are no modes and no patterns? And it's basically a publication I had a few years ago where I described how you should do this. So first of all, what you have to be aware of that every pattern exists in your data. If you have your global sea level pressure data of many, many months, hundreds of years or so, basically every pattern exists. And this just mathematically, what it means is that you can define a pattern pi, let's say a smiley face, a triangle, or whatever kind of pattern you like. You project it onto your data. You project this vector onto your matrix, and what comes out is a time series. And this time series will have an amplitude. It will not be zero. Right? If you have data, you can project any pattern onto your data. It will have a time series. It might be meaningless, but the time series will not have zero amplitudes. If it doesn't have zero amplitudes, you can actually define and explain variance related to this time series and this pattern. So you can actually define and explain variance, and it will not be zero. Whatever pattern you put into your data, you can project it onto the data and ask questions, how much variance would I explain by putting this pattern into the data? A triangle, a smiley face, or whatever you like. Every pattern exists in the data. And the question is not whether a pattern exists, but the question is more how much variance does it explain? So the question really is, how does the pattern relate to the others? Is it relatively strong? Is it stronger than expected? And then, of course, the question is, what is expected? And what kind of physical process can cause this pattern if it is unexpected from some kind of a simple expectation? So really the question, and when you deal with data analysis and searching for patterns, the question is not whether a pattern exists. The question is, how strong is the pattern? How does it relate to some kind of simple null hypothesis? Is it unexpected, this pattern, to explain that much variance? So really the question is, how much variance does my pattern explain? And is this unusual? Is it unexpected? To understand this a little bit better, I think it's nice to compare the way that we analyze time series with the way that we compare patterns. So if we have a time series like this one, this is the El Niño 3 time series over 50 years. So you see these chaotic fluctuations, and you want to describe this type. You have the idea that this is a continuous process, a continuous stochastic process, and you want to find some interesting structure in this, maybe an oscillation. So typically we look for something, is there something oscillating in this? And in El Niño we know there's some kind of a 4 years oscillation in it. It's relatively weak, but there's not just noise. So this here is not just noisy red noise out of regressive process order 1, but there's actually some damped oscillation going on. In pattern analysis, we have these large chaotic pattern of, can I start this? I think this will not work. No, it will not work. But you see this chaotic, I showed you this before on Monday, these chaotic fluctuations, and you wonder, is there some structure in it? So you are asking for something like this, is there some teleconnections in it? In time series analysis, we have actually a very nice concept. We have the idea of this red noise. We have the idea that my time series might be a stochastic process, that my variable is a damping that just gets it back to the normal state. So it's a negative feedback, linear feedback, and you have some white noise forcing the system. So we have this idea of a stochastic null hypothesis, this red noise idea. And if you want to find something interesting in the time series, what we often do is we do a power spectral analysis, compare it with the red noise, and then we see here the black line is above the red line for for a large region. That indicates it's something is going on. There's something oscillating probably on the interlinear timescales. So we have a concept of starting with the idea there's nothing, it's just red noise, and then we find the difference by saying this power spectrum shows me an oscillation. There's more interlinear variance here, so there could be an interlinear oscillation going on in the Niño 3 tropical Pacific region. In pattern analysis, this concept doesn't really exist. So if you go with pattern analysis, we assume that our data matrix at any time t is just a time series multiplied by patterns. So that's the way that we think of it's created by patterns. And there may be a residual which is not so important, and this residual is just noise, chaotic thing. But we are interested in these patterns that create the data. And our current approach is to figure out a smart statistical method to define these patterns. And there's many of these methods. Principal component or EOF are the most popular ones, probably the most widely used ones. But people use all kinds of methods to define these patterns. But that is different from the way we treat time series. I think what we should do is formulate a null hypothesis. So asking the question, what does the noise look like? What do we expect for the noise if there are no patterns? So we should formulate a stochastic null hypothesis for the noise. So to understand the way that why we are approaching these things differently is we have to understand why is time series analysis different from pattern analysis, and what do we do differently, and how we could then maybe have a similar structure. Nevertheless, there are some differences between these two. So the difference is in time series analysis we have a power spectrum which are harmonics, sine function and cosine functions. And we fit these harmonics to the data, and we have our power spectrum which is based on harmonical orthogonal functions. In pattern analysis we don't do this. We have the empirical functions, the principal components. And this is motivated by some characteristics that are different in time series analysis and pattern analysis. First of all, in time series analysis, we can have an infinite time series. Right? We can measure temperature at Melbourne, and we can make our time series infinitely long. And basically, our time dimension is not limited. It can be endless. Right? So our domain limitations doesn't really exist in time series analysis. So we can have oscillations of very low frequencies, very large oscillations can exist, and our kind of smaller scale can exist. So there's no domain limitations. While in pattern analysis, there are domain limitations. An ocean basin has a boundary. The Earth is just a certain size and can't be bigger than that. Right? So there's boundaries. And if you think about, you have these boundaries, there's certain harmonics that could just not exist. There's no oscillation larger than the Earth in the Earth. Right? There's a largest oscillation. And that would be just the Earth doing the same thing at the same time everywhere. That is the largest pattern that can exist in the Earth. So there are some boundaries of what kind of functions we could actually fit to our data, because there's a boundary. The other difference is stationarity. So stationarity assumes that all your statistical parameters are always the same at all points in your domain. On a time series, if you have your time series, you assume that the spread is the time series everywhere the same. You assume more or less it's a stationary system and the mean is always the same, which is not quite true because we know there's a seasonal cycle and sometimes the variability is stronger in winter and less in summer. But in principle, we assume that this doesn't matter that much. It is not influencing strongly our results, and usually that is true. But if you analyze a basin like the Pacific, or this northern hemispheric sea level pressure, that stationarity is really not given anymore, because the variance is very different in the tropical Pacific from the North Pacific, or in the hemispheric view of sea level pressure, there's much more variance at the pole than there is in the tropics. So the stationarity is really not given with patterns. And I think this is why, because of the domain limitation of the stationarity, this is why we like these empirical functions, because they automatically somewhat put these non-stationarities into these harmonical functions. But nevertheless, even though we have these differences, we look at empirical functions here, and here we look at harmonics, we can still follow the same strategies. We can formulate a hypothesis and a null hypothesis. So the hypothesis in time series is that there's oscillation going on. So we are looking for oscillations, for damped oscillations maybe. And in the hypothesis in pattern analysis, we look for coherent teleconnections, coherent patterns. The null hypothesis, so basically the opposite, would be, in time series this exists, is the red noise IR1 process. That basically means linear damped. This is our null hypothesis in time series. In patterns, so if you have this null hypothesis, we basically compute our power spectrum from our data and from our theoretical null hypothesis, and we compare them, and the differences are the ones that is interesting. The null hypothesis in patterns doesn't really exist in the literature. If you look at the literature, you will find one publication that actually states, this is my own publication, there really is no null hypothesis for patterns. But I think it's a useful concept to do this also, that we have a null hypothesis. And I basically formulate a null hypothesis and explain it in the next slides, which would also be red noise, but spatial red noise. And its physical process would be isotropic diffusion. That just everything is chaotically mixing and there's no structure. And then you would use, again, a spectrum, but not of harmonics, but a spectrum of these patterns, and look at these patterns. And I'll explain to you now a little bit how you actually formulate this null hypothesis red noise for patterns, and how you then apply it to actually figure out teleconnection patterns. Okay, so how do we formulate the stochastic null hypothesis for spatial structure of damped variability? So what is the spatial IR1 process like? And again, this is based on my own publication. It's not really a concept defined in any textbook, but I think it's quite useful when you look at this. So isotropic diffusion, if you write down a tendency equation, let's say you have a physical variable, you have a tendency equation, you would usually assume a very simple way, if you're not knowing what's going on, you would assume there might be some local damping, thermal radiation, or just local damping. And there will be, where's my mouse? There will be diffusion. So you have the second derivative of your horizontal field. That basically tells you what kind of maximas and minimas are there, and there will be diffusion will act to reduce maximas and minimas and mix everything out, smooth out everything. And then you have a diffusion coefficient here that tells you how strong the diffusivity is. And then you might think about this system might be forced with random white noise. So random white noise means white in time, so every time you throw around a number, but also white in space, so that every different location gets a different forcing. If you think about this kind of a physical system, you can actually show that this is an autoregressive process of order 1. That means in spatial, that means the spatial derivative, dx. So previously in time series we had d dt, but now here d dx, so the spatial relationship of your field is a constant multiplied by the field plus some white noise. And that is the definition of an IR1 process, basically. So you have a linear damped system, but now in space, so linear damped in space, and some white noise in space dimensions. And since you know autoregressive process of first order was that the spatial autocorrelation, so we had the autocorrelation with lag time, but now we have distance in space. So this lag correlation would be exponentially decreasing. So it's an exponential function which is decreasing with a decorrelation length of d0. So basically you would assume that any point at a location would be correlated to all the other points, and if the distance gets larger, the correlation will become smaller. There's no anti-correlation, it's only positive correlations. And you're correlated to nearby regions and not correlated to remote regions. I think somewhat we all have this in our mind as our null hypothesis if you look at data. And if you look at data, I'll give you here examples. So on the left column, you see sea surface temperature, 4 examples. On the right column, you see 500 hectopascal geopotential height. What I just do is here, I do a correlation of this box with the sea surface temperature everywhere else. And then I take another box, and here another box, and here another box. And I think what everybody knows is that if you correlate something, then of course nearby regions will have high correlations. So you see, if you are close to this box, you have high correlation. If you are far away from this box, you have almost no correlation. So roughly speaking, this idea, you can see that as diffuse system, nearby regions are highly correlated, and remote regions are not correlated. But you can also see there's differences from that, right? For example, this point here has a negative correlation here, and then at a remote region there's a positive correlation. So correlation goes down and then goes up again, which is not what you expect. Correlation should only go down. So you see there's some structure that goes beyond this, and these are the structures that we are interested in. These are our teleconnections, our pattern. Or you can see here in this one, here in the tropical one, you see there's correlation decreasing to the south, but it's much faster decreasing to the north. So there's an interesting anisotropy. So it's not just isotropic in all directions the same, but there's in one direction there's strong relationship, in the other direction there's less of a relationship. So you can see structures in this that are interesting. And these are probably the structures that we are thinking about teleconnections. Here the right column shows you the same example with atmospheric 500 hectopascal geopotential height. And again, you see here in this point, nearby regions are positively correlated and remote regions are not correlated. Same here. Here it's quite different. You see that all the tropics are highly correlated and it's highly anisotropic. And here's another point, which is somewhat a mixture. So you see somewhat this diffusive idea is correct, but there's deviations from this diffusive idea. There are structures that go beyond isotropic diffusion. For example, here's a negative correlation, and here's also a negative correlation. So there's interesting structure in this. But overall, you see, to first order, I can say it is somewhat diffusive, but it's not all diffusive. If you look at EOFs of this process, the EOFs look like this. It's a monopole, dipole, dipole, tripole. It's a hierarchy of multipoles, basically. Quite more or less geometrical function. It depends on your domain how they actually look like. But there's a certain order in this that how the diffusive process would look like in EOFs. And then here to the right, you see the eigenvalues decreasing more or less exponentially. But there's some structure in this. So there's no uncertainties here. So there's real structure in this thing. This depends again on the geometry of your basin, of your domain. So why is the EOF? So first of all, the first thing you can say is EOF number 1 is a monopole and it has to peak in the center. Why does it peak in the center? Because this point here has the largest covariance with all other points because it's closest to all other points. If you have a diffusive process, then the central point will be the one which is highly correlated or covariant with all the others. No other point will have as much covariance. So this is why the first mode has to peak in the center of your domain, or where the most variance is. And it will be positively related to all other points because the only relationship that really exists is positive correlation. So the first mode has to be a monopole, and it has to center in the center of the domain. And if you look then at the other EOFs, really, they're all multipoles, right? So they're all suggesting anti-relationships, but in a diffusive process, everything is only positively correlated. There are no anti-correlations. So you can't interpret any of these modes as teleconnections. So none of these EOF presents coherent teleconnections, except for the first one, the monopole. Actually, the way that you should look at these things is more like they represent spatial scales, like in a power spectrum, that the low frequencies and the high frequencies. So the first mode is the low frequency, it's the largest scale. The second mode is the second largest scale. Oops. And the first mode has the largest scale, has more variance, and the smaller scale has less variance. In a diffusive red noise process, larger scale will always have more variance than the smaller scale because everything gets smoothed out, and small scale deviations, small contrasts will be damped out. So the red noise in a spatial sense means larger scale will have more variance and smaller scale will have less variance. So these EOFs are not interpreted in terms of coherent teleconnections, but just saying different scale variance. And the EOF number 2 is this dipole here along the larger axis, because these two regions are very remote to each other. So they represent a large scale, far away regions, and in order to be orthogonal to the first one, they have to be those two regions that are the least related to each other, because they have to compensate for the monopole in the first EOF. It's a constraint by the orthogonality. So if you think about your data as nothing but red noise, you will see monopole, dipole, dipole, tripole, quadrupole. And just look at EOF analysis that you see in the publications. You will see always this structure. You see always monopole, dipole. That is the general structure that you see in EOFs. And it just comes from this diffusive thing and the geometry of your domain that you look at. Now, if you look back at our literature examples, these high-profile publications, 3 of them are EOF number 2 being a dipole. Right? These are all EOF 2s. They are all dipoles. And in principle, these are trivial structures. Right? If you know nothing about your data and you think it's just noise, EOF number 2 will be a dipole. So my main concern about these high-profile publications is that these structures are trivial. They follow from noise. EOF number 2 dipole is basically a representation of noise. There might be something else into it, but first of all, just looking at this, it's a trivial structure. The Arctic oscillation is somewhat more difficult because the first EOF is not a monopole, but it's this kind of angular mode. But if you think about sea level pressure as a constraint of conserving mass, sea level pressure cannot go up everywhere at the same time. And the largest variance in the northern hemisphere, where's my mouse, is at around the Iceland and the North Pole. So if you think about you have a monopole, an increase of sea level pressure at the poles, this is what the diffusive process would suggest, where the center of the domain, where the largest variance is, it has to go up and down in a monopole-like structure. Then there has to be, in terms of sea level pressure, conserving mass, there has to be a negative anomalies around it. So basically, if you consider diffusive processes and conservation of mass, then an angular mode is trivial. This is what you expect as EOF number 1. It's not suggesting anything sophisticated. Right? It is. So my main concern with these current literature examples is that they are trivial structures. They follow from noise without any interesting dynamics behind it. So we have now formulated a noise null hypothesis, and the noise null hypothesis is this hierarchy of multipoles. It's isotropic diffusion, red noise. So how do you look at EOFs if you do this? So I think what you can do now is you compare your EOFs. You have your observed data, and you can compare it simply with this null hypothesis of red noise. And then you see what the interesting structures are. So how do you compare spatial patterns, let's say EOFs, from a dataset A to a dataset B? Or what we want to do here first is compare our EOFs from a dataset with our spatial red noise. How do we do this? It's a bit more complicated than the power spectrum. So in time series, we had the power spectrum. We look at the red noise power spectrum fitted to it, and then we see the differences. There's one more step in between that we have to do, and that is because we have empirical modes, and each dataset has its own set of modes. We have to define a common set of modes. So usually what you can do is you can define the EOF modes of your one dataset, let's say dataset A, as your reference. These are my reference modes. And then you have to project the other dataset onto that. That is simple algebra. You can just either project the whole data matrix on it, but it is actually simpler when you just use the EOFs of your dataset B, and you project the EOFs of dataset B onto the EOFs of dataset 1, A. And these are then your reference mode. What you get from this projection is basically explained variance values. So what you actually get is you can compare now the eigenvalues of your dataset A with your projections from dataset B. So what you would get here, you get your power spectrum here of eigenvalues. Let's say the black ones are the eigenvalues from your dataset A. And then you project your other dataset or your theoretical null hypothesis red noise onto it, and you see how much variance do I actually expect from those other dataset or from red noise. And then you might see this, here's number 2 that has much more variance than I would expect, or that the other dataset has, and then that would be an interesting structure in dataset A. So in principle, it's very similar to the way you do it with time series analysis. So I think it's the same approach. So you fit an AR1 process red noise to your data. So in time series analysis, we did this by knowing the standard deviation and the decorrelation lengths. We can do the same thing with patterns. Decorrelation lengths and patterns is more complicated, but I don't want to go into this. But you basically do the same thing. You know the decorrelation lengths, you know the standard deviation, or like one correlation here in terms of decorrelation lengths. Then you would know your red noise process. You have your power spectrum of the time series, which is the black one. You fit the red noise to it, and the deviation from that is the interesting part in your data. You do the same things in patterns. You have your covariance matrix. You compute your power spectrum, which is EOF values, which are the black dots here. You compare the red noise, which is the red dots. You project it onto these EOFs, and you see there might be a deviation. This pattern number 2 is the interesting pattern. So in spectrum, you would say here's an oscillation going on, and that oscillation has a period of 4 years, like El Nino. And here you would see that this pattern number 2, which happens to be here a dipole, is the interesting pattern of your data. I'll show you an example. So I create myself an isotopic diffusion process, and on top of it, I put a forcing pattern, which is a dipole. I choose a dipole because it looks like noise, and I want to show you that you can actually distinguish a dipole from noise if you do it the right way. And I choose it to be not dominant, so it's not EOF number 1. I choose it to be relatively weak dipole pattern, forcing pattern that we want to find by looking at the data. So we have our constructed data, and then we compute the EOFs of the data. In that case, it's a monopole, dipole, and dipole. So it looks more or less like noise. It looks like isotopic diffusion. And then we project our null hypothesis, assuming that it's only pure isotopic diffusion. So we would get our monopole, dipole, dipole. So first of all, they look similar. But then the question is again not whether a pattern exists. The question is how much variance does the pattern explain. So you have a certain, you do not only have patterns here, but you have a certain amount of variance that each of these patterns explain. And the null hypothesis, the isotopic diffusion, would tell you how much variance each of these should have. So you then have your variances from your data, so from these data modes to data EOFs, and then you compute how much variance does the null hypothesis would have for these patterns. And then you get the red dots. And in that case, you would see, actually expect a little bit more variance in the monopole, and this structure should have more variance if the null hypothesis would be true. The second pattern, this dipole pattern, should actually have less variance than you observe in your data. And then you can basically see that this would be then my interesting pattern. So I would ask the question, which of these is maximizing this difference? And this is my interesting pattern. And in that case, it would be the dipole. So actually, I find the dipole. And I can then here, there's a small number written in here. You can hardly read it. It says 80%, 10%. That first number says 80% of variance is what this pattern has in my data set. But I would only expect 10% if the null hypothesis were true. So I can at least say that there's about a certain part of this pattern which is not expected from noise. There must be something else. So I would know that there's a forcing pattern in it. Okay, so the strategy would be, instead of just taking the EOFs as you did in this deterministic mode view, you would compare the whole structure of the EOF modes all together. You would look at the power spectrum and see whether there's deviations. And if there are large deviations, you would ask the questions, which pattern is maximizing this deviation? And these are my interesting teleconnections. This is probably the approach that I do when I do EOF analysis. And I think this is the way that you can find interesting teleconnections. And I show you 2 examples from the real world where we probably all agree on what the teleconnections mode should look like. So let's take the tropical Pacific SST. And I think we all agree it should be an ENIO pattern coming out, because we know that this is a real teleconnection, a real mode going on. And I do tropical sea level pressure, where I think we probably all agree that the southern oscillation is something dominant in the tropical sea level pressure variability. So let's see how this works. So EOFs from the tropical Pacific look like this. EOF number 1 is this El Nino kind of structure. EOF 2 is this, depends a little bit of what kind of data you look like. Sometimes these two flip around. Sometimes this is EOF number 2, and sometimes this is EOF number 2. But in that case here we have this kind of negative here and positive everywhere else. And then the other one is the so-called El Nino Modoki pattern. going to the left and right and a little bit to the north. The null hypothesis isotopic diffusion, of course, is a monopole, and it has centered where most of the variance is. So where my standard deviations are large, then the pattern has the center there. Second mode is a dipole. Looks a bit similar to this dipole here of Aninio Modoki. And then the third one is a tripole pattern. And then you make this projection. And if you, the black ones is against observed eigenvalues, so my EOF number 1, my so-called Aninio pattern, would explain more than 40% of the variance. And if it would be just isotopic diffusion, I would expect this pattern to explain only half as much. So it's somewhat as unexpected that this pattern here has so much variance, if it would be just noise. So my analysis would tell me that this pattern number 1 is the most interesting pattern. And if I maximize the difference, actually it's this pattern that is the most interesting pattern in the Pacific, which I think most people would agree on, that Aninio is something along the equator, and the center part of the Aninio 3.4 region is actually more the one that's predictable. That is the real oscillator. So basically, it somewhat shows that this method works with things that we know we all agree on, basically. Let's look at sea level pressure in the tropics. And it might be a little bit hard to see, so I go from about 10 degrees south to about 10 degrees north. So here's Australia, the maritime continent, Indonesia, then here's South America, and then you'll see Africa somewhere here. Okay, if you look at EOFs from sea level pressure, it depends a little bit on what data set and what time length, but the first EOF is actually a monopole. It's not the Southern Oscillation Index. The second EOF looks like the Southern Oscillation Index, with negative in the Pacific and positive over the maritime continent. And then the third pattern is another dipole. So it's, the domain is around the Earth. So you have to connect the left part with the right part. So it's again another dipole, but just shifted by 90 degrees. And if you just null hypothesis would actually look like quite similar. You would also have, of course, a monopole. That's the first one, a dipole, and another dipole. But the order of the dipoles is somewhat shifted here. And if you compare this, that analysis would tell you again that the second mode here observed is more variance than you would expect from isotopic diffusion. So this pattern here is the one that seems to be the interesting one. And if you do optimize this, it is indeed the Southern Oscillation Index that comes out as being the interesting pattern. Although it has also a connection to the Atlantic here a little bit. So summarizing the stochastic continuum view. So I think we can deal with the patterns the same way that we deal with time series. So we, just as in time series, we can think of the spatial variability as a stochastic continuum, as red noise. Right? A single EOF mode has no meaning as such. It can only be understood in the context of the whole set. A single EOF, like in a power spectrum, you can't pick out a single cosine or sine function. It really has only a meaning if you know the whole power spectrum. It's the continuous function, basically. And in the same sense, a single EOF has no particular meaning at the beginning. Maybe later on we have figured out that there's something interesting, but at the beginning, first of all, a single EOF has no meaning. Since in an isotopic diffusion, everything is positively correlated, there's no negative correlations. You can't interpret these EOF modes as coherent teleconnections. They are more a reflection of different scales. Larger scale is monopole, smaller scale is multipoles. So they're more a reflection of how important are certain scales in your domain. If you have your first EOFs all be very large scale, that means your domain is dominated by large scale modes. If you have your first EOFs all be small scale structures, then you have smaller scale of variability. It's not about teleconnections, so these modes would more reflect like the scales of and how much variance they have. And the null hypothesis would be red noise, the same as for time series, but it's spatial red noise. And physically it means isotopic diffusion. And spatial red noise is represented in EOFs in a hierarchy of multipoles. So monopole, dipole along the direction where there's the most remote regions. And red noise has no teleconnections, right? Other than just the trivial one that everything is positively correlated. But there's no other teleconnection than that. Interesting teleconnections or more complex dynamics that might be interesting are those that deviate from our red noise. So those structures that are not fitting into the idea of spatial red, these are the structures that are actually the true teleconnections. So this is the thing, I think, the way that is efficient of looking at the data. You can, of course, also take the other view, the deterministic view. Both ways are possible. You are more likely to fall into the trap of thinking there's coherent teleconnections if you take this deterministic view. On the other hand, if you do the stochastic continuum view, you would think everything is noise. Right? You will probably not get a Nature paper, but I think both are probably relevant. So in conclusion, just shortly, I think principal component analysis is a very sophisticated trick, but you might eventually lose the ball. Right? I mean, it is very likely that you actually do something and you have totally lost it. You are thinking of teleconnections that are non-existing, and it's very likely that you mess it up. So be careful. I mean, it's a very good trick, but you have to be careful when you're applying this. This is all that I say for conclusions. So basically, you have the conclusions for the deterministic view and for the stochastic view, and overall you have to, it's a very good technique to find these patterns, but you have to be very careful when you apply this. Okay, coming back to where we started. So initially I asked you this question. If you have EOF number 2 being a dipole between region A and B, how do you look at this? Huh? The deterministic view, I would tell you that probably there's a monopole teleconnection as EOF number 1. I think it's very likely that our points are scattered like this, and these two, region A and region B, are positively correlated. It's very likely. I don't know how EOF number 1 looks like, but I think in 9 out of 10 cases, EOF number 1 is a monopole. So I think very likely these region A and B are positively correlated. From the stochastic continuum view, we know noise has EOF number 2 a dipole. So if it's red noise, then EOF number 2 would be a dipole like this. Very relatively remote regions with an anti-correlation. And if it's just red noise, then these two centers mark regions that are mostly unrelated, right? But they have a small positive correlation, assuming it's just noise. So which statement is true? It's statement C. The community, 99% of all professors in atmospheric science and ocean science would go for A. And you don't see any publications that state C, but C is true and A is wrong. In 9 out of 10 cases, this is true. Right? So it's this unusual case that if you have an EOF number 2 and you know nothing else, it is likely that A and B are largely unrelated, and they might have a small positive correlation. Because of isotropic diffusion, always having this pattern, and also because if EOF number 2 is a dipole, probably EOF number 1 is a monopole. And if there are two teleconnections, then the monopole teleconnection is the more important one. Okay, that's the finish.